Hello everyone, and welcome to this Spacewalkers live session, on which I will present EVPN Overview, Fundamentals and Positioning. My name is Abu Bakr Dongola, and I am a Network Solution Architect working for the Network Business Division at Alcatel-Lucent Enterprise. Let us begin. Let's look at the agenda. I will start with a recap of VxLAN technology with its strengths and weaknesses. Then I will go through the basics and fundamentals of EVPN along with advanced features of EVPN, such as multi-homing, MAC mobility, and more. After that, I will go through the ALE implementation of EVPN and what makes it unique. Then we will start the hands-on demo, and I will close with some key takeaways. Let's begin. So VxLAN is a standards-based technology. It's a layer 2 overlay technology that is used to encapsulate and tunnel traffic through a layer 3 underlay IP network. It's primarily used in data center or cloud network infrastructures. It encapsulates an Ethernet frame received from a host into an IP packet with a UDP header of destination port 4789. Then it forwards the packet on a layer 3 network. Using UDP is beneficial for flow load balancing and load sharing due to the hashing. So each segment is identified with a VNI or VxLAN network identifier, which is a 24-bit number that identifies a VxLAN segment. This provides a namespace of about 16 million segments. The switch or host that performs the encapsulation and is the termination point of the VxLAN segment is called a VTAP. VxLAN is a point-to-multipoint technology. So there are multiple options to run VxLAN in your network. One option is to directly use leaf switches for VxLAN encapsulation. In this case, the leaf switches are called the hardware VTAP. The second option is to use a software-based VTAP, where the VTAP is configured on your hypervisor, which is the case when using overlay-based SDN technologies such as VMware NSX or NewEdge. You can also use a hybrid option in case you have legacy or bare metal servers that do not run VxLAN technology. So what are the key strengths of VxLAN? First is the ability to extend layer 2 over layer 3 boundaries, and layer 2 extension is key for use cases in data center, such as vMotion, and in the case of campus network for IoT and Wi-Fi roaming. Second, it's not required to run spanning tree protocol on your core network, since the underlay can use a dynamic routing protocol for loop avoidance. Third is that scalability is not an issue in VxLAN, since the limit is pushed from the standard 4096 segments up to 16 million segments. It's also improved since there is no MAC learning in the core, but only on the VTAPs. Also, it provides underlay isolation and multi-tenancy. So VxLAN alone is a data plane concept. It's not intelligent enough to dynamically learn endpoint reachability information and relies on data plane learning. So let's look at a few weaknesses that VxLAN has without the use of a control plane protocol. First, in terms of BOM replication, there are two methods. BOM stands for broadcast, onion unicast, and multicast. So there's two methods. The first is to use head-end replication, which replicates the BOM traffic once for each receiver and sent as unicast. It's inefficient in terms of bandwidth utilization. The second option is to use tandem replication, which is dependent on a multicast-enabled underlay and requires manual mapping and configuration of the underlay, which increases the complexity. Second weakness is that VxLAN relies on flooding to learn end host MAC information. So the local host MAC addresses are learned on the local SAP ports, and the remote MAC addresses are learned on the VTAP SDP ports. Also, from the service point of view, VxLAN services without a control plane are pure layer 2 services. It does not support inter-service layer 3 routing. Another issue is that it does not support multicast snooping in the control plane. Also, VxLAN does not support VTAP multi-homing, that is, connecting a host to two independent VTAPs with a link aggregation for load balancing and redundancy. This, of course, can be done with virtual chassis technology on OmniSwitch, but this is not the case if independent VTAPs are required. Lastly, there's also the potential traffic trombone issue, where a VM has been moved to the target data center needs to communicate with VMs or clients in the source data center. So in this scenario, additional network traffic has to be pushed through the DCI or WAN connections between data centers. These are some of the issues that can be solved using a control plane protocol such as EVPN. So in the data plane, VxLAN encapsulation is used, and it's running over a layer 3 IP underlay and using headend or tandem replication. So what are the control plane options that can be implemented in VxLAN to solve most of its weaknesses? So first, you can use static or manual configuration of the VNI segments on the VTAPs. This can be simplified with automation or a management platform, but it's limited in terms of scalability. Second is to use a software-defined control plane options such as NSX, or Nuage, or OpenStack. The control plane is managed through a centralized controller. The third option is to use MP-BGP Intelligent Control Plane Protocol like EVPN. So let's talk about EVPN. So MP-BGP EVPN is a control plane protocol for VXLAN based on RFC 7432. EVPN introduces a new address family, EVPN, to the MP-BGP protocol family. The EVPN NLRI is carried in BGP using BGP multi-protocol extensions with an AFI or address family of 25, which is for L2 VPN, and SAFI or subsequent address family identifier of 70, which is for EVPN. The main objective of EVPN is to build ELAN services similar to other VPN technologies while supporting MAC learning within the control plane, which is distributed by MP-BGP. MP-BGP EVPN can be used with multiple data plane option technologies such as VxLAN, MPLS, PBB, and more. So the first data plane option is using network virtualization overlays such as NVGRE, VxLAN, and MPLS over GRE. The second option is supported by PBB, or Provider Backbone Bridging, which uses MAC and MAC encapsulation, which is similar to SPB. The last encapsulation option can be MPLS. So in this presentation, we're focusing on EVPN with VxLAN. So what are the benefits that EVPN brings to the table as a control plane protocol? First, EVPN allows for a single unified control plane protocol that supports layer 2 and layer 3 VPN services. It has many use cases, whether in the data center, the DCI connections, the campus, and more. It also allows for seamless integration. Also, the key features of EVPN, such as multi-homing, aliasing, ARP suppression, mass withdrawal, distributed unicast gateway, and MAC mobility, provide an efficient network fabric that easily scales. We will discuss these features later in the presentation. Since EVPN is based on a BGP, which is a proven and stable and scalable protocol. Also, EVPN can run on multiple transport technologies, such as VxLAN, MPLS, PBB, and more, as we've discussed earlier. So this provides flexibility to the user. It's also a standards-based technology supported by many vendors, which allows for interoperability. EVPN also allows for a better security and control through the granular admin control and the delivery of multi-tenanted services across a shared infrastructure, using concepts such as VRFs, VNIs, route distinguishers, and route targets for segmentation and control. It also has network-wide visibility of host attachments. In addition, EVPN also solves issues mentioned earlier, such as VTEP multi-homing and traffic tromboning through the distributed unicast gateway functionality. So let's go through a few key terminologies for EVPN. The first one is EVI, or Ethernet Virtual Instance. This is represented as the VNI in EVPN VXLAN, which is a broadcast domain or a VPN. The next one is ESI, or Ethernet Segment Identifier. This is a mandatory, globally significant 10-byte encoded value which identifies the Ethernet segment. It's usually equal to 0 when the CE is single-homed, and non-zero when multi-homing, but this is based on the RFC. As you will see later, the ALE implementation for ESI for single-homed connection is non-zero value. The ESI is MAC-based and can be auto-generated for both single and multi-homed LACP host. The next term I want to discuss is ETAG, which is the SAP port configured broadcast domain, such as VLAN. It can also be auto-generated as per ALE implementation. We also have the MAC VRF, which is a VRF table for CE MAC addresses stored on a PE. There's also concepts of designated forwarder and integrated routing or bridging, which we will discuss later in more details. There are different EVPN ETAG service interfaces as mentioned in RFC 7432. The first is a VLAN-based service model where you have a one-to-one mapping. So you will have a dedicated VLAN, which will go to a dedicated MAC VRF, which will go to a dedicated VNI, which will go to a dedicated EVI. So in this case, VLAN translation is performed where the incoming tag is stripped off on the ingress PE, and the VLAN tag is added on the egress PE. So this will allow for overlapping MAC addresses across the VLANs. But there's a single broadcast domain per EVI. The second one is the VLAN bundle service. It has a many-to-one mapping. So you have multiple VLANs, which will go to a dedicated MAC VRF, which will have a dedicated VNI, which will have a dedicated EVI. So this means a single broadcast domain and MAC addresses must be unique. So the receiving device will import everything because of the route target, even if the VLAN does not exist on the device. So the SAPs are configured with untagged or wildcard value, and the incoming tag is carried end-to-end as it is. The last model is the VLAN aware bundle service, where many-to-one mapping is performed. So you have multiple VLANs which will map to a single MAC VRF, but it has multiple switching table. And this goes to separate VNIs and will go to the same dedicated EVI. So this allows for separate broadcast domain per EVI. And VLAN translation can also be performed and MAC addresses can overlap. ALE current implementation is based on the VLAN aware service model. So let's discuss a few EVPN route types which are displayed on this slide. The key route types used in basic EVPN are type 2 and type 3, which are highlighted in this slide. So the first one is, let's go briefly over the route types. The first one is route type 1, which is used in multi-homing for advanced features such as aliasing and fast convergence. There's also two subtypes of type 1, route type 1A, which is used for Ethernet auto-discovery route per ESI, and route type 1B, which is for the Ethernet auto-discovery route per EVI. We will touch on those in the multi-homing sections. The next route type, which is the most important one, which is route type 2. So this is used to advertise the MAC reachability information between the PEs or VTEPs. It can optionally advertise host IP addresses as well. It's used in features such as ARP suppression or proxy ARP. Route type 3, which is called the Inclusive Multicast Ethernet Tag, or IMET route, is used for the auto-discovery of remote peers to set up the bump tunnels, or also called the ingress replication list, over VxLAN. This is done by exchanging information about the location of VTEPs on a per VNI basis. The next route type is route type 4, which is also used in multi-homing scenarios. It's used to discover VTEPs which are attached to the same ESI and used for designated forwarder election for bump traffic handling. We will discuss the designated forwarder election later in this presentation. The next route type is route type 5, or IP prefix route, which is used to advertise IP prefixes rather than MAC or MAC IP as advertised in route type 2. It can be used for external communications and to summarize routes such as default route. It also provides the ability to provide L3 VPN services. The last route types 6, 7, and 8 are used for multicast snooping and multicast optimization. Type 6 is used to distribute multicast traffic join request, while type 7 and 8 are used to synchronize IGMP join and leave information between multi-home peers. So EVPN also uses the concept of route distinguisher and route target in its BGP update messages. Route distinguisher is an 8-byte ID of a VRF, since each VRF has its own unique route distinguisher in the network. So when an EVPN advertisement is sent out to the peers, the route distinguisher is attached to the route to make it unique in the network. This allows for the route to be unique in the network. This allows different also VRFs to use overlapping IP addresses. The route distinguisher can be automatically defined to simplify the configuration. So EVPN uses type 1 route distinguisher, which uses the loopback and router ID to generate the route distinguisher. As a reminder, type 0 uses the autonomous system number with colon N. The route distinguisher, it can be ESI based or EVI based or VRF based. Then we have the route target, which is an extended community in EVPN route updates, which is used to control route distribution in a multi-tenant network. So EVPN PEs have an import and export route target setting for each VRF and each VNI. When a PE advertises EVPN routes, it attaches its export route target in the route update. So the route will be received by other PEs in the network. The remote PEs will compare the route target value carried with the route against their own local import route target setting. If the two values are matching, the route will be accepted and programmed into the routing table. Otherwise, it will not be imported. So the route target can be automatically also defined to simplify the configuration. It can be EVI or ESI based. So how is endpoint reachability information learned and advertised throughout the EVPN domain? So when the service is first enabled, route type 3 or IMET route is used to build a flooding list after discovering all the PEs attached to the same broadcast domain. In this case, PE1 discovers that PE3 is in the same broadcast domain using route type 3. This is saved in an ingress application list stored on each PE. So when the VM first starts communication and the PE receives the first frame, it looks at the destination MAC address. If the address is a multicast or a broadcast address, the PE floods the frame across the service using the ingress replication list generated earlier using route type 3. This is done by encapsulating the frame with the VxLAN headers and using the VNI available in route type 3, and then sending it over VxLAN data plane. If the destination address is a unicast address, the PE searches the corresponding MAC VRF table for a matching entry. If there is no match, which is usually the case in the first frame, then the destination address is unknown and the PE will flood the frame. It will store the source MAC address in the local MAC VRF table and advertise this MAC address to the remote PEs through route type 2. In case the PE can snoop the IP information through control plane protocols such as ARP or DHCP, then this is also advertised in route type 2. So layer 2 bomb traffic can be flooded in two ways in a VXLAN fabric. The first one is head-end replication using EVPN route type 3, which is also called ingress replication. The ingress PE will replicate the frame per each interested remote PE and will send this traffic as unicast. So route type 3 is used to establish the ingress replication list or bomb tunnels. Head-end replication is very simple to configure, and it already has inbuilt loop prevention features such as split horizon. The other one is to use tandem replication, which uses a multicast-enabled underlay network. The PEs will require a mapping between the VXLAN VNI and the multicast group IP address, so this method is more efficient than head-end replication since only one copy of the frame is sent. The ALE AOS EVPN implementation is based only on head-end replication for EVPN. So another key benefit of EVPN is its ability to perform multi-homing efficiently. So there are two redundancy modes which are available, all active or single active. In all active mode, every PE device associated with a specific ESI has the capability to forward traffic. This ensures that the CE benefits from load-balanced and non-blocking connectivity. This will require link aggregation LACP to be configured on the CE and on both peer PEs. This is for loop prevention and to avoid any duplicate packets. EVPN route type 4 is used for discovering peer PEs, which are part of the same ESI, and will also be used for assigning a designated forwarder for that segment. So how is bomb traffic handled in multi-homing scenarios? A designated forwarder has to be elected to avoid duplicate bomb flooding to all active CEs, and it's also responsible for bomb flooding into the Ethernet segment. So each PE in a multi-homed Ethernet segment builds an ordered candidate list only if route type 1 is received from that PE. So the default algorithm used is a modulo-based algorithm, which is the EVI modulus n, where n is the number of PEs in the EVI. So in this example, since we have two PEs in the EVI, it will be calculated for EVI 10 as follows. So 10 modulus 2, which is 0. So the first PE in the candidate list is selected as a designated forwarder for EVI 10. So by default, the designated forwarder election is preemptive, so it is recalculated when a PE is added to the candidate list. Unicasts will still be allowed both paths for all active multi-homing, but only the non-designated forwarder will block the bomb traffic. So in this slide, for example, PE1 is elected the designated forwarder for EVI 10. Any remote bomb traffic coming into PE2 for that service is not flooded into the Ethernet segment, since it's not the designated forwarder for that EVI. Service carving also allows to elect multiple designated forwarders per Ethernet segment to perform load balancing of bomb traffic destined to a given segment. It can also provide a designated forwarder per EVI as opposed to a designated forwarder for all the EVIs. At the same time, split horizon rules ensure that bomb traffic sent to the non-designated forwarder is not replicated back to the ESI. So how does split horizon work? The ingress PE will add a ESI label to the bomb packets, which identifies the originating Ethernet segment. So the egress PE will check the received BOM packets. If the packet includes an ESI label that was allocated to the locally attached Ethernet segment, the PE does not forward the packets over this app. Otherwise, BOM packets are properly forwarded to the Ethernet segment if the PE is the designated forwarder. Also, local bias feature allows the local interface to be preferred to reach multi-home segment. For example, VM1 to VM2 traffic will be preferred through PE1. Another feature of EVPN is aliasing. So aliasing is a feature which allows load balancing of unicast traffic from remote PEs to the local PEs, which are part of the same ESI. EVPN advertises what PEs are part of the ESI using route type 1 Ethernet auto-discovery routes and the redundancy modes such as all-active multi-homing. The MAC addresses are advertised to the remote PE using route type 2, and the remote PE then does load balancing to all the ESI owners, and the ESI is set as the next hop for the learned MAC addresses. In case the ESI is all active, then the remote PE performs flow-based load balancing to all the PEs. If it is configured as single active, then it sets the designated forwarder for the ESI as the primary PE, and the non-designated forwarder as the backup. This helps with fast convergence, as we will see in the next slide. So in case there is a failure in an all-active multi-homing scenario of the PE-CE link, then the PE will withdraw the route type 1 auto-discovery per EVI route to alert the remote PEs. In this slide, PE1 and PE2 advertise that they are connected to ESI 1234 using all-active mode. PE1 and PE2 then learn the local MAC address of VM1 and advertise this using route type 2 MAC IP EVPN route to the remote PE3. So the advertised MAC route indicates that VM1 MAC address is in ESI 1234. PE4 learns the VM1 MAC address through route type 2 and concludes that it can use ESI 1234 as the next hop to reach the VM1. So with ECMP enabled, PE3 can then load balance the traffic destined to VM1 to both PE1 and PE2. If a link on an Ethernet segment fails, the attached PE withdraws the route for its connectivity to the ESI. The remote PEs then learn about the failure. Assuming we are using a single active redundancy mode, the remote PE moves the next hop of each MAC address associated with that ESI to the backup VTAP. So there's no need to wait for each individual MAC route withdraw. In the slide above, when the link to PE1 fails, PE1 withdraws the EVPN route for its connectivity to ESI 1234. PE3 then moves the next hop of all the MAC addresses associated with ESI 1234 to PE2, the backup PE for ESI 1234. EVPN supports host mobility across Ethernet segments. If a MAC address becomes reachable in multiple segments, EVPN tags the route type 2 MAC IP advertisement routes with the MAC mobility extended community, which includes information necessary to decide which of the competing MAC advertisements to use. So this feature is particularly beneficial during seamless host migrations, such as vMotion. So the MAC mobility sequence number is used to keep track of where the endpoint is attached. In this slide, PE1 advertises an EVPN route type 2 with a connected MAC address, AABB. So once VM1 moves to PE3 and the PE3 realizes that the MAC address is learned on both locally and through the remote EVPN fabric, it sends an updated route type 2 with the MAC mobility extended community and it increments the sequence number. PE1 will eventually withdraw the all MAC address. There's also some protection features which are implemented, such as the threshold and hold timers, to absorb any impact of rogue host mobility in the EVPN network. One of the benefits and optimization features of EVPN is the ability to allow PEs to act as a proxy and respond to local ARP request or IPv6 neighbor solicitation messages to reduce or suppress the flooding produced by them. This reduces the BOM traffic flooding in the fabric. In the route type 2 MAC IP advertisement route, you can optionally carry IPv4 or IPv6 addresses associated with the MAC address. So the PEs, they built proxy ARP or neighbor discovery tables per EVI with the MAC IP information received from locally snooped control packets. For example, ARP or gratuitous ARP or neighbor discovery or EVPN or even static entries. The PEs reply to ARP or neighbor discovery request or solicitation messages that they receive. So in this slide, PE1 receives the gratuitous ARP from VM1. It learns the MAC address AABB and the IP address 192.168.2.10. Then it advertises both addresses in a MAC IP advertisement route to remote PEs. PE3 then imports the route for the EVPN service, then adds an entry in the associated proxy ARP or neighbor discovery table. When VM2 sends an ARP request to learn the MAC address associated with the VM1, PE3 receives the ARP request and consults the proxy ARP neighbor discovery table that it maintains for the EVPN service. Then it will reply back with an ARP reply message to VM2. So PE3 is no longer required to replicate the message and flood it to the remote PEs. EVPN also supports the configuration of a distributed Unicast gateway, where each service has a common default gateway with a virtual IP, virtual MAC address, which is configured on all PEs, all peer PEs of a multi-home CE. So there are two routing models defined in RFC 9135 for integrated routing and bridging, asymmetrical and symmetrical. But what is integrated routing and bridging? It's a solution based on EVPN which allows for dynamic and efficient inter-subnet connectivity among VRFs and the end devices while maintaining the multi-homing capabilities of EVPN. So instead of sending all the traffic to a centralized layer 3 gateway in a data center use case, even if two hosts that belong to the different subnets are connected to the same PE, they are instead routed in the local PE using integrated routing and bridging capabilities. In the asymmetrical routing model, the ingress PE performs a MAC lookup and does layer 2 switching to the gateway IRB interface, and then also performs an IP lookup and does layer 3 routing to the destination IRB interface. Again, after the layer 3 routing, the ingress PE again performs a MAC lookup and does layer 2 switching to the destination VNI. The egress PE performs only a MAC lookup and does layer 2 switching to the destination host. So this will require, of course, that all services to be configured on all PEs, even if no hosts are attached to the PE. This does have a benefit of less control plane load since only route type 2 is used in the core. On the other hand, in the symmetrical model, both the ingress and egress PEs performs layer 2 bridging and layer 3 routing. The ingress PE performs a MAC lookup followed by an IP lookup, and the egress PE performs an IP lookup followed by MAC lookup. This will not require the service configuration in all PEs, but only where the hosts are attached. This is more scalable, but will require route type 5 to advertise the IP prefixes. So there's two symmetrical configuration models. The first one is to perform host routing. The second one is to perform prefix routing. In the host routing model, only MAC IP routes are used. However, this is not a scalable option since it will require to advertise host routes instead of prefixes. The other and preferred model is to use prefix routing and advertise prefixes using route type 5 since any prefix length can be advertised, which provides flexibility. There are different multiple prefix routing models for symmetrical routing, as mentioned in RFC 9136. The first one is interfaceless VRF to VRF model. Second one is interface-full VRF to VRF with using a supplementary broadcast domain, IRB model. And the third one is interface-full VRF to VRF with unnumbered supplementary broadcast domain, IRB model. So the ALE implementation in the initial release will support asymmetrical IRB. So multicast uses route types 3, 6, 7, and 8. Route type 3 is used in general for BUM replication, while route type 6 is used for support of IGMP or MLD proxy functionality and to distribute multicast traffic interest by host for StarComG and SComG. In case multi-homing is configured, IGMP state information can be lost whenever there is a link failure. Route type 7 and route type 8 are used to synchronize IGMP state information between multi-homed hosts. There are two modes to handle multicast traffic. Either use route type 3 IMET routes or use route type 6 SMET routes. The IMET route will allow a host to receive all multicast traffic, while the SMET route allows a host to receive multicast traffic on request. SMET routes provides multicast optimization and minimizes IGMP traffic in the core. So now I will highlight the design of ALE EVPN model. So AOS EVPN model has been designed based on simplicity, scalability, and stability. As you will see later in the hands-on demonstration, the AOS EVPN model has been designed with minimal switch configuration to initiate the EVPN operation on the service and access ports. You also have the ability to instantiate an ESI for any EVPN-enabled access port type, depending on that type of port. So for example, physical access ports automatically default to single home connection, while link aggregation links default automatically to multi-home single active. Another simplicity feature is the auto-generation of ESI, the E-tag, the route distinguisher, and the route target. This allows for EVPN operations to be easily orchestrated for the SAP ports. RFC also 7432, it specifies that the ESI value should be 0 for single-homed connections. ALE, however, we add a value to the ESI for single-homed connections. This will add the same benefits of multi-homed connections to single-homed connections, including mass withdrawal. This also increases the scalability and provides better performance because there is less network traffic in the core and more network visibility and convergence time. This is interoperable with other vendors. The EVPN route advertisement, such as updates and withdrawals, they follow a specific order of operation. So this maximizes the efficiency of the operations. Also, EVPN in AOS uses an on-demand model for the data plane, which will help to vastly improve the data plane scalability and convergence by avoiding having to store in hardware any unused or undesired destination host entries. All routes are only imported to the forwarding database or the forwarding information base based on an on-demand model where bidirectional traffic is required to be generated to see the MAC addresses in the forwarding database. The AOS EVPN model also uses summarized route updates and withdrawal for operational events of the route object, which results in a rapid forwarding database updates and faster convergence. Another advantage is the optimized forwarding database updates for the multi-home single active ESI, which allows for efficient mass withdrawal and failover. Now let's look at the lab topology we will use, and then we'll start with the hands-on demo. As you can see in this topology, we have 3 VMs which are configured in different VLANs. Client 1 is in VLAN 950, client 2 is in VLAN 960, client 3 is in VLAN 970. So CE2 and CE3 have been configured for LACP link aggregation for single active multi-homing towards the PEs. We will be only demonstrating single active multi-homing in this demo. CE1, on the other hand, is single-homed on the physical port of PE2. Distributed Unicast Gateway has been configured on PEs 1 and 3 for client 1 and PEs 3 and 4 for client 2. You will see this configuration later on. The client devices have been pre-configured with the Distributed Unicast Gateway virtual IP address as the default gateway. I recommend to take a screenshot of this topology to follow along with the demonstration. So let's begin. I will be performing the EVPN configuration on PE1 and PE3 for this demo. Currently, the only configuration I have which is available is the underlay configuration. So we can check it out here. I have the configuration of the loopback address, which is the same address I'm using for the router ID. I have the point-to-point connections between the PEs, which I'm using as routed interfaces. I have also enabled OSPF in the underlay with point-to-point network type, which is best practice since no DR or BDR election is required. For BGP, I am using iBGP, Single Autonomous System Network, in our topology. I'm using the normal IPv4 unicast address family, iBGP peering, and did not enable EVPN BGP NLRI updates for the EVPN address family. As you can see also, there's no service manager configuration on the switch. I should mention also that CE switches are already pre-configured with the LACP link aggregation required for this demo, and the only configuration I will do is in the PE switches. We can verify also the same configuration in PE3 as well. So the first step is to enable EVPN advertisements for the BGP routing process. By default, it's usually disabled. So what we need to do first is we need to disable the BGP protocol. Then I will enable EVPN advertisements. Then I need to enable the exchange of EVPN routes between the BGP peer routers. So we'll do it for PE2. We'll do it for PE3. And we'll do it for PE4. Finally, after this is done, I will then enable the BGP protocol again. So now I can verify that the BGP neighbors are up. They have been established. And of course, it's also established to PE3 because we have not disabled the protocol yet. So let's do that. We will activate the EVPN. And we will enable the exchange of EVPN routes between the BGP routers. Finally, we will enable the BGP protocol again. We can verify that the BGP neighbors are up. They have been established. We can also verify that the EVPN address family is activated and advertised for each neighbor. So let's do that. As you can see here, the activate EVPN has been enabled and the neighbor is advertised. The next thing I will do is to configure the LACP link aggregation as per the configuration performed on the CE side. So on PE1, we're supposed to configure link aggregation 10 with port number 1-1-51A. So I'll do that. In P3, I have two ESI connections, one for lag 10 and one for lag 20. So let's configure that. Lag 10 is using port number 1-1-3, and lag 20 is using port number 1-1-4. We can verify the configuration. As we will see later, since I have configured link aggregation, this will default to single active multi-homing ESI type without any configuration from our side. On the other hand, in PE2, I will configure EVPN for a physical port, so it will default to single-homed ESI type. The next step is to provision EVPN VxLAN services and discovery. Before performing this step, I should note that in PE1, PE3, and PE4, I'm using a dummy active interface 1/1/1 to allow all the EVPN services to be up. This is because I'm using asymmetrical integrated routing and bridging, which requires that all services to be initiated and up in all the PRPEs. In my case, I'm using port 1/1/1, which I will configure as a dummy port. The next step is to enable Ethernet segment operations on an access port. When enabled, this allows EVPN Ethernet segment configuration and functionality on a service access port. So I will enable it first on the dummy port. Then I will enable it in the link aggregation port. Next, I will enable BGP EVPN operation on our services. I'll use 3 services, one for each VLAN. So service 100, 200, and 300. Service 100 will use VNI 1000. Service 200 will use VNI 2000. Service 300 will use VNI 3000. Next, I will create the SAP ports for our services. I will start with the dummy port. Then I will create the real SAP port. We're using service 100 for the real SAP port, using the link aggregation and VLAN 950, which is for client 1. On PE3, let's do the same configuration, except there's 2 Ethernet segments in PE3. Then let's enable the services. also on the dummy access port. And let's enable the real services. And then we'll enable the dummy service. Let's verify our configuration. As you can see, we have three services, three subports, one for LinkAG 10, one for LinkAG 20, and one for the dummy port. Service 100s are activated. Service 100 is using VNI 1000, service 200 is using VNI 2000, service 300 is using VNI 3000. And we have the LinkAG services because we have two real services, and the rest are for dummy ports. So now that we have established the services, we will verify that the EVPN services are up and confirm the number of SAP ports configured. So the command is show service EVPN. As you can see, the services are up, and we have two SAP ports here. There's one SAP port per service because of the dummy port, but the actual real SAP number is only one. We can verify the same here as well. We can also verify the details of the Ethernet segments, local and remote, operational on the PE. We can use this command. As you can see, the Ethernet segment type defaulted to multi-homing single active without any configuration from our end, since we are using link aggregation port, which you can see here. And this is the ESI number, which we will be using later in our other commands. We can also verify the MAC VRF table, and there are types generated so far. As we can see, there's no MAC addresses learned yet, since there's no bidirectional communication established between the hosts. Since AOS uses an on-demand model, this will greatly improve the scalability. We can also verify the route type 2 generated. So this is the command. So what you can see now is in the table is the IRB interfaces configured on the PE switches for each EVI, as you can see here. They're configured on the remote switches. But this doesn't contain any of our hosts. We will compare them later once the full configuration is done. We cannot test them yet as we have not configured the gateway yet. So we can verify the SAP details of our ESI. So let's copy the ESI and show service EVPN Ethernet segment. SAP info. So we can see that this is single active multi-homing. We can also see the ETAG values and the route target as well, or the EVI. We can also see the local PE is the designated forwarder. We can also verify this information using this command, which shows the service carving, the carving information. So let's copy this. As we can see, since we are using single active multi-homing, there's one designated forwarder only, and no non-designated forwarders. We can also verify the route type 4 generated, which discovers which PEs are attached to the same shared Ethernet segment and for DF election. We can also check the route type 1A advertisement, which is for auto discovery per Ethernet segment route. It's used to auto-discover Ethernet segments and identify the list of PEs associated with an Ethernet segment. It enables also mass withdrawal and includes the ASI label required for split horizon. It will also indicate the redundancy mode. So this is the command to check it. As you can see, the Ethernet tag must be set to the maximum value of all Fs. We can also check the route type 1B, which is for the Ethernet auto discovery per EVPN instance. It is used to advertise the Ethernet segment availability in a given EVPN service. It's also used for features like aliasing and primary and backup lists. Let's also verify the route type 3, which is used to discover remote PEs, which are part of the same broadcast domain, or EVI. We can see also the tunnel encapsulation, since we're using VxLAN, which is number 12. It will also show the status of the IGMP and MLD snooping, since it's disabled. So let's proceed with the configuration. Next, we will configure our integrated routing and bridging interfaces on both PE1 and PE3. And next, we will configure our distributed Anycast gateway virtual IP, which will be used in our host as the default gateway. So let's configure first one service per interface on PE1, and then the same in PE3. So the same in PE3 as well, but a different different IP address. The next step is to configure our distributed Anycast gateway addresses on PE1 and PE3. So first, we will configure the Anycast gateway to auto-derive the MAC address. So let's do that. Then we will configure the distributed Anycast gateway interfaces. We'll do the same in P3 as well. So let's verify the Anycast IP configuration. So we can see here the Anycast gateway address is configured, and we can see the router MAC address and all the details. We can do the same for the other services as well. We can also verify the Anycast virtual MAC address. So now that everything is configured, we can verify the connectivity between our clients. Let's first verify our IP addresses. We can see here that this is configured with the IP address 10.10.95.50. And let's check the other client. This is configured with 96.50. So let's first of all ping our gateway addresses, which is the Anycast gateway address. Seems to be working fine. We can check it on this side as well. Seems to be working fine. So now let's ping between client 1 and client 2. So on client 1, I'll first ping this one. It will not work in the beginning because we require bidirectional traffic. So you will notice in the beginning there was a slight delay with the ICMP pings before the successful pings. This is because of proxy ARP, which from both ends, and based on the on-demand AOS EVPN model. So once this is established, the communication is established, we can verify the MAC address table, the MAC VRF table. So show MAC learning. We can see here that we're learning on the SAP port the MAC address already for client 1. And we're learning from the other side from client 3, service 200, we're learning the MAC address from the other side as well. As we can see here, we cannot yet see it here on the subport. This is because it's using single active multi-homing, so it might have been, the designate forwarder might have moved to PE4 because this is automatically generated. Yes, we can see this in the subport configured here on PE4. We can also verify the rod type 2, if rod types was generated or not. As you can see here, rod type 2 was generated for the client 1, and it should be also generated for client 2. Yeah, as you can see here. And we can also see that it also learned the IP address as well, which was snooped from the packets directly. And this was communicated through rod type 2. So the last feature I want to show is proxy ARP. Proxy ARP is enabled by default, and we can verify this using this command. We can see here that shows complete ARP suppression is enabled. We can also check the proxy ARP table using this command. As we can see here, the proxy ARP table already includes client 1, which was communicated to the other PEs as well. Yes. We can also view the proxy ARP statistics as well. We can see what is local and what is remote as well. This brings us to an end of our demo. Let's close with some key takeaways. EVPN allows for a single unified control plane protocol that supports Layer 2 and Layer 3 VPN services. It has many use cases in data center, the DCI, campus, and more, and allows for seamless integration. So key features of EVPN, such as multi-homing, aliasing, ARP suppression, mass withdrawal, distributed NCAS gateway, and MAC mobility, they provide an efficient network fabric that easily scales. Also, EVPN is a BGP-based overlay protocol, which is BGP is a proven and scalable protocol. The AOS EVPN model is based on simplicity, scalability, and stability. Simplicity is provided with the automated features and the ease of configuration. Scalability and stability is obtained through efficiency mechanisms, such as the on-demand model. EVPN also allows for better security and control through the granular admin control and the delivery of multi-tenant services across a shared infrastructure, using concepts such as VRFs, VNIs, route distinguisher, and route targets for segmentation and control. It also has network-wide visibility of host attachments. MP-BGP also provides flexibility by being able to run on multiple transport technologies such as VxLAN, MPLS, PBB, and more. It is also a standards-based technology supported by many vendors, which allows for interoperability. So thank you for attending this session.